So thank you very much, Serena, for the introduction, and also thank you all for the invitation to speak today. Yeah, I'm from Wageningen University, and today I'm going to tell you a little bit about organic micropollutant degradation and sorption during drinking water treatment. But before I jump completely into that, I wanted to do just one slide introducing our department. Our department really works on environmental technology, so we're an environmental engineering group. And we have kind of three main aspects, so three main subgroups. We have the biorecovery group that really looks at all sorts of technologies to recover valuable components from waste streams and using different types of processes for this. So bioelectrochemical systems, novel fermentations to produce precursors for chemicals, and also biocrystallization processes. Then we have our reusable water group where we look at different technologies to produce clean water. I, of course, work in the micropollutant and pathogen group, but we also have people working on granulation, on desalination using CDI and stuff like this. And then finally, we have what we call our urban system engineering group. And there we look at how to really implement these technologies into real urban environments. So what type of, we do quite a bit of modeling to be able to understand material flows in real urban systems and identify what are the hotspots for waste streams or for contaminants or for recovery and reuse technologies. So to really be able to implement these in the urban environment. So that's kind of our group in a nutshell. I'll be speaking today, of course, about organic micropollutants. And I'm going to do this actually by first giving a short introduction to drinking water systems in the Netherlands, because I think they're quite different to some extent with what currently occurs in Switzerland and maybe many other countries. Then I'll say something about biodegradation of micropollutants in groundwater, and then finally about removal in rapid sand filters. So a little bit about the Netherlands. You can see here a map of the Netherlands. We have a lot of rivers, so we're really the drain of northwestern Europe in a way. You can see here in, is this working? Yes. You can see we have the Meuse River that comes in from Belgium. We have the Rhine River that comes in here from Germany. So we have quite a bit of water coming into the country. And then it sounds kind of strange to say water scarcity, right? Because we're known as a very water-rich country. Nonetheless, for drinking water production, we do have quite some challenges. And the major challenge is actually drinking water production along this coastal area. Because this coastal area, you can't use groundwater due to seawater intrusion. And so all along the coastal area, we use surface water and collect that surface water and retain it in different ways along the coast. So one of those is through dune infiltration. You can see here a picture of it. These are these locations shown in orange, so all along the edge here. So each of those dune infiltration locations, we pump in surface water infiltrated through the dune. And that acts as some treatment, but also acts as a reservoir of local water. And then additionally, we have surface water reservoirs. So you can see here in this, we call it the Biesbosch area. So this is an area here, so just east of Rotterdam. And there you have these surface water reservoirs. You can see them here as these reservoirs. And there they also take in surface water and store it in the reservoirs. And then in some cases, we also have to do quite extensive transport. So this whole southern portion of Zeeland, so this province in Zeeland is all salt water. So all of these inlets are salt water. There's no real fresh water available there. And that means that they transport water 100 or 200 kilometers to the south. So all of these reservoirs are very nice because we have a local source of clean and, or sorry, I should say a local source of fresh water. Unfortunately, it's not always clean water, right? Because it's coming in from all of these surface water intakes. And so one of the nice things about the reservoir is that at least you have a reservoir of water. You can monitor the river water quality. If you see changes in your river water quality, you can stop intake to your reservoir and you at least have that reservoir. But as I said, we do have quite some challenges related to organic micropollutants in these water sources. You can see here a summary from KWR, so that's a research institute in the Netherlands, and they looked at micropollutants in surface water intakes and reservoirs used for drinking water production. And you can see on the left the number of compounds above the detection limit, and on the right the number of compounds above regulatory limits. And you can see that in some cases there's tens of compounds detected and quite a few at concentrations above drinking water regulations. And overall, approximately 70% of the surface water intakes contain some sort of micropollutants that are above drinking water regulations. This is, of course, very seasonally dependent, right? In the summer, you have more concentrated water, so it's higher concentrations than in the winter. So that's for the surface water used along the coastal area. And then the rest of the country, so the whole eastern part of the country, produces their drinking water from groundwater. So you can see all of these groundwater extraction locations shown in blue. So there's 150 some odd groundwater extraction locations across the eastern part of the country where drinking water is produced. And most of those locations look something like this. This is a simplified scheme, but you can see here kind of a typical drinking water aquifer in the Netherlands. You have an array of pumping wells that are pumping up water, abstracting water for drinking water production. And in the Netherlands, we have almost no groundwater flow, so we're very flat layers of sediments. So natural groundwater flow is 1, 2, 3 meters a year. But at these drinking water aquifers, then because of the high pump rates, you really control the local hydrology. So the water is drawn in. And this, of course, is for drinking water companies very nice. You have quite a bit of water available. And drinking water companies are, of course, also very interested in knowing future quality of that water. And that's why around all of these production wells, they install these types of monitoring wells. So monitoring wells filtered at discrete depths, so you can monitor the water quality. And they typically measure hundreds of different micropollutants. So they screen for a whole collection of micropollutants. And what they see due to infiltration of surface water and application on land is then a whole variety of especially pesticides present, but more and more pharmaceuticals and personal care products also. You can see here then some data related to this. So they looked a couple of years ago, KWR again, this research institute, looked at the number of compounds in the abstraction wells themselves. So these are the wells actually producing the water. And you can see on the left, a handful of compounds above the detection limit. And fortunately, as you can see on the right, not so many compounds above drinking water regulations. This is for the abstraction wells. So based on this, you can say there's no acute problem for micropollutants. But if you were to look at the monitoring wells, so these monitoring wells are telling the future quality of the water. And there you can see that there's tens of compounds already detected at these locations. So that means while we don't have an acute problem, we will in the coming decade or so. And this is really a concern for drinking water companies, of course. So if we put all of these data together, then you can see here a map of all the drinking water production locations in the Netherlands, and you can see quite a few of them have concentrations of pesticides above drinking water, EU drinking water regulations, or approaching drinking water EU regulations. So we really, we know these compounds are there, and we know we have, if not an acute problem, at least a future problem. And this problem is kind of exacerbated by the way that we produce drinking water in the Netherlands. So as I said, we have approximately 150 some odd drinking water production locations where we use groundwater. And those locations really have the philosophy of having very clean water and therefore very simplified treatment. So you can see here, really it's just abstraction from the aquifer. There's some aeration, possibly some softening depending on the water quality, and a sand filter, and then the water goes for distribution. So there's currently at all these locations no extensive sorption or oxidation technologies present. And of course, if you needed to implement this at the 150 some odd drinking water treatment plants in the Netherlands. This is a very big cost. So yeah, quite a big challenge if this was necessary. And that's why for a lot of my research then, we look at how can we treat micropollutants already in these existing systems. And one side of that story is then trying to understand what type of transformations could occur in the groundwater before abstraction. So how can we somehow understand bioremediation or implement bioremediation in the groundwater itself? And then the other side of the story is trying to understand what could happen in these rapid sand filters. So in the sand filter itself, can some of these compounds be removed? And to what extent could they be removed? And how could we also improve that? And I explained this, I think, very much from a, let's say, applied perspective. Drinking water companies have a challenge, but I hope to also show you today that these are quite interesting systems also to try to understand biodegradation processes and to understand what type of conditions are required for this, what type of substrates, substrate loading rates, contact times, et cetera, are required to understand this. So I'll start out by going into the groundwater side of the story, and I'll give you a little more background on these drinking water aquifers. So here's kind of again, a simplified schematic of an aquifer. So you have your extraction well here in the middle that controls the local hydrology. So it's drawing in groundwater, and that results, of course, in infiltration from the surface. And then we know that with this infiltration, there's a whole set of micropollutants that can come in. In addition to those organic micropollutants, we also have dissolved organic carbon, so natural dissolved organic carbon infiltrating. And we know from various studies that this dissolved organic carbon is to some extent biodegraded in the groundwater. And that means that you have a gradient in the concentration of the DOC, but also to some extent in the quality of the DOC with depth. So shallower groundwater has more easily degradable, higher concentrations of dissolved organic carbon, and the deeper groundwater has lower concentrations, less easily degradable carbon. Additionally, we have a whole variety of redox conditions. So I spoke with some of you today. I understand now Swiss groundwater is really oxic. In the Netherlands, we have mainly iron and sulfate reducing conditions. So we normally have maybe a very small nitrate reducing layer at close to the surface, but most of it is iron or sulfate reducing. So we have different kind of a gradient of redox conditions in the groundwater. And what we've shown in other studies that I won't really speak so much about with today is that this selects for quite diverse microbial community that's really depth dependent. And what we showed in previous research is that community is to a large extent selected by which electron acceptors are available, a little bit based on DOC concentration. And we saw some indications that there could be slight selective pressure by the organic micropollutants, but in the study it was hard to see if this was a co-correlation or not. But we know then we have a diversity of conditions, we have a diversity of microbial communities. So one of the first very straightforward questions we asked ourselves was, can these microorganisms do anything? So do they have any capacity to biodegrade micropollutants, and under which conditions? And we anticipated a very oligotrophic groundwater, therefore low microbial biomass, low microbial activity. And so we just wanted to see, can we expect anything out of this groundwater, or should we go in a different direction? And so we started with a quite straightforward study where we collected groundwater from a drinking water aquifer, and we used that as an inoculum of a microbial community, so the natural groundwater microbial community. To it, we added a number of different micropollutants. We did this study at quite high concentrations, as you'll see in a moment, but because we really wanted to screen, is there any potential for biodegradation at all? And then in some cases, we added a little bit of dissolved organic carbon extracted from compost. And in some cases, we also shifted the redox conditions, so changed it compared to what was in the field. And here's a little data to give you some kind of feeling for this Dutch groundwater. So you can see here, we tested 10 different groundwater samples. And they varied in depth quite a bit, so from 13 down to 50 some odd meters, so a variety of different groundwater depths. You can see they had a variety of different redox conditions naturally, so some of this groundwater had nitrates, so it was nitrate reducing. Other groundwater had iron 2 present, so most likely iron reducing. And then you can see that there was also, I see that these jumped a little. You can see that there was also a variety of DOC concentrations. So depending on depth, we saw more than 10 milligrams per liter of carbon down to around 3 or so milligrams per liter of carbon. So like I said, a straightforward screening, we took this water. We had some conditions that were just blanks. So we just took the water as it was, added micropollutants. Some of them we added DOC. Some of them we also added an electron acceptor, so either oxygen or nitrate reducing conditions. And to just go briefly into some of the results. So here I show the results for 3 groundwaters that were kind of representative for all 10 groundwater samples that we tested. And what we saw was surprisingly no degradation for MCPP or BAM, which we had expected to see at least some degradation, but we didn't see that. We did see biodegradation of 2,4-D, so it's a pesticide. We did not see it under any natural groundwater conditions, and we actually found that in all conditions we needed to add both oxygen and DOC in order to see biodegradation. And that was, for me at least, kind of surprising because we know 2,4-D is a relatively biodegradable compound, and I would have expected that it could at least be degraded under aerobic conditions. And what we saw here is that oxygen alone was insufficient. You also had to add an additional carbon substrate, so add this additional DOC. So that was kind of surprising to us. We saw a very clear depth dependency for the rate at which 2,4-D was degraded. So you can see here a set of samples with the red one. So they're in order of depth. So the red one is the most shallow and the blue one the deepest. And so you can see really the shallow groundwater seemed to be the most active. So the rate of degradation in the shallow portion of the aquifer was faster than in the deeper samples. So from this kind of first screening, then we could clearly see that, yes, there is potential for 2,4-D biodegradation. So groundwater does have some activity for micropollutant biodegradation, but based on the fact that we saw so limited degradation, it seemed like maybe microbial biomass in the groundwater may have also been to some extent limiting, so that the groundwater itself was just too poor in biomass to really see significant degradation. One thing that we did think was interesting was this DOC side of the story. So as I said, the natural groundwater contains DOC, and that DOC was apparently insufficient to support biodegradation, and we really had to add then additional easily degradable DOC to see biodegradation. And so that kind of led to our next question, which is, what is the role of this DOC in micropollutant biodegradation? So to what extent is this DOC required, and what are the characteristics of that DOC? And we were kind of working on this hypothesis that there's some sort of co-metabolic biodegradation or co-substrate usage for the DOC in these oligotrophic groundwater conditions. So our kind of assumption is that natural groundwater is very oligotrophic. That means you have low concentrations of poorly degradable DOC, kind of signified here as the gray DOC. And that creates a type of famine conditions in your aquifer. So you have low microbial activity and therefore very low micropollutant degradation. And so what we saw in that study that I just showed is if you add a small amount of easily degradable DOC, in that case, DOC extracted from compost, then you see more activity and therefore more micropollutant biodegradation. And our idea is at least that if you go too far in this, so if you add a lot of easily degradable DOC, you kind of shift the microbial community towards utilization of that easily degradable DOC and shift them away from micropollutant degradation. So you have a selective pressure for degradation of that easily degradable DOC. So finding the nice middle ground in between these two conditions, that's the real challenge. And we know that because if you look at concentrations, we expect that this DOC is really the selective pressure on our microbial community, that the low concentrations of micropollutants present are probably not high enough to be a selective pressure. And so our hypothesis was really that DOC biodegradability is the key factor that supports or inhibits micropollutant biodegradation. So that it's not so much, to some extent, it's about the quantity of DOC, but is especially about the quality of the DOC that determines that. And so we did a set of experiments where we tested this. We collected microbial communities, this time from aquifer materials. So we collected sandy aquifers from approximately 30 meters below ground level. And we put those in batch experiments with a variety of organic micropollutants under aerobic conditions based on our previous study. And then we had kind of 4 different DOC conditions. So in one case, we said we don't add any DOC. And then we added humics as a, let's say, poorly degradable DOC source. In another set, we added dextrin. Dextrin is a glucose polymer, so it's somewhat degradable DOC, but not easily degradable carbon. And then acetate as kind of like the extreme, very easily degradable carbon. So we tested these different conditions with this microbial community from the aquifer sand. And as you can expect, we saw very clearly that depending on our DOC source, we also saw different microbial activity. So you can see, you can see here on the left, the DOC consumption. And as we expected, our acetate and dextrin were very easily removed. So they were very quickly degraded in the system. And our humics actually were not significantly degraded, maybe a slight removal. And this was really linked also then to respiration, as you can see with acetate and dextrin addition, much more oxygen consumption and CO2 production than without it. And so our expectation was that this would then also be linked to differences in micropollutant biodegradation. And what we interestingly found was actually this was not always the case. So here's an example of 2 compounds that were degraded, which links to a number of other compounds that were so for 2,4-D and chlorodisone. And you can see that actually, regardless of the DOC biodegradability, we see somewhat similar kinetics in degradation. So we don't see a difference in either the timing or the rate of degradation, and also not in the final concentration. So it seems that for some compounds, DOC biodegradability is really not important at all. For one compound that we did see some potential effect was for MCPP. So you can see here, without DOC addition, we saw a little bit of degradation. We also saw quite some variability in our triplicate samples, but it seemed like there was less degradation without DOC than if we did add DOC. Once again, the biodegradability of the DOC didn't seem to matter. So we saw similar results with humics versus acetate versus dextrin. And I think quite interesting in this was also that we saw the kind of a cutoff for MCPP biodegradation at around 40%, which corresponded in our study to around 18 micrograms per liter. So there was kind of a cutoff there. And after that, we saw no further degradation, which maybe could be related to some sort of metabolic cutoff was our idea. So to this question, what is the role of DOC? It seems like it really depends on the micropollutant. And I'll show in a little bit some more studies that also kind of confirm this, that the role of DOC really depends on the microbial community and which organisms are doing the degradation, and most likely relates to their metabolic strategy. So from all of this, then we kind of came to the conclusion that regardless, we need oxygen to support micropollutant biodegradation in groundwater. Most likely, depending on the compound, a little bit of easily degradable DOC is required. And then the next question is, how can you really engineer this, right? So we're talking about groundwater systems, 40, 50, 60, 80 meters deep. How can you How can you engineer this micropollutant biodegradation in situ? And so our first kind of idea was to look at how could it be combined with a technology that's already applied in the Netherlands. And what's already done in the Netherlands in many locations is subsurface iron precipitation. So like I said, Dutch groundwater is anaerobic, so it has quite iron-reducing conditions. Therefore, it has quite a bit of iron too present in the water. And some locations, they pump up the water, aerate it, and then use filters to remove the iron. But you can also imagine you can try to precipitate it in the groundwater. And this is done commonly, not across the country, but in some locations. So basically, they infiltrate oxic water. That oxic water then spreads in the aquifer and causes iron oxide precipitation. And then you can abstract the water afterwards, and it is iron-free, essentially iron-2 free, much lower iron-2 concentrations than beforehand. And the advantage of this is, of course, iron reduction takes much more pore volumes than iron oxidation. So you can inject basically 1 pore volume of oxic water to remove the iron, and you can abstract 20 to 30 pore volumes of iron-free water afterwards. So it's it's not a 1-to-1 now, it's 1-to-20, 1-to-30 ratio. So this is already done, and we thought, oh, this could be a very interesting system because we have, for micropollutant biodegradation, because we're creating aerobic conditions, right? You're injecting oxygen. In theory, you could also inject a small amount of DOC at the same time if you wanted to, so that's not so hard to engineer. And the other interesting thing is groundwater also naturally has ammonium in it. So you're mixing ammonium with oxygen, and then you would expect a little bit of nitrification activity, which could, as we know, could be good for co-metabolic degradation of micropollutants. So for this research then, we were really curious to see if this was possible, and we thought one of the big limitations of these systems is really the oxygen concentration. So we know the oxygen is really rapidly consumed by the iron, and therefore we really expect trace concentrations of oxygen. So one of our big questions was, with this trace oxygen concentration, is that enough to support micropollutant biodegradation? And then again, what is the role of DOC and possibly nitrification in this system? And so for this, we collected samples again from the field. We spiked them with 23 organic micropollutants. This time it's now nearly environmentally relevant concentrations. It's a little on the high side still, but close to environmentally relevant concentrations. In some of them, we added dissolved organic carbon. Sometimes we added ammonium. Sometimes we added a little bit of iron-2 to see the competition between iron-2 and oxygen. And then kind of our biggest variable was the oxygen addition. So we had high oxygen concentrations of around 1.5 milligrams per liter. We had low oxygen concentrations of 0.4 milligrams per liter. And then we had a situation where we added oxygen a couple of times to see if you're dosing just small amounts of oxygen, as you would expect in these heterogeneous systems. Do you also see that? So we were really trying to play with the oxygen availability. And to jump into the results, so we saw that many micropollutants were biodegraded. So this was actually quite a nice study from that perspective. I'm showing here results from after just 3 weeks. The student working on this, her experiments are ongoing, so hopefully with time maybe we'll see a little more degradation. But you can see here is that degradation really depends on the initial oxygen concentration. So on the far left, you have the high oxygen concentration. In the middle, you have the repeated addition, and on the right, the low addition. And you can see under high addition, and we really see most of the degradation. For certain compounds, you see under repeated oxygen addition, some degradation, and under low, you see much less. So this really says that the oxygen availability seems to determine micropollutant biodegradation, but it also shows that under these low oxygen availabilities, we still do see transformation. So that was very nice to see. The other question was, what is the role of DOC addition? So you can see here for a number of compounds, their removal efficiency over the course of the experiment. and for different conditions. So we had a set of conditions where we added DOC and iron together, DOC and iron and ammonium, DOC and ammonium, and iron and ammonium. And basically all of the ones in solid bars are the ones with DOC, and the one in the slashed bars are the ones without DOC. And what we saw was for many compounds, the addition of a little bit of DOC improved the biodegradation. So for all of the compounds highlighted now, we saw that addition of a small amount of DOC improved degradation compared to the condition without DOC. So this confirms what I get once again, that small amounts of DOC seem to stimulate microbial activity and therefore also biodegradation. We also looked at the role of ammonium. So this is actually the same data, but then the first bar is the crossed one because that's the one without ammonium. And what we actually saw that nitrification, or the presence of ammonium, I should say, did not really seem to support biodegradation. So we didn't see improved removal under conditions with ammonium. And that's most likely related to our nitrification activity. So if you look at the ammonium removal data, then we saw relatively low removal of ammonium. So most likely really an oxygen limitation for nitrification activity. So that could be why we didn't see real biodegradation under a bean. That's why we didn't see improved co-metabolic degradation due to nitrification. So back to this engineering question. So how can we engineer this micropollutant biodegradation in groundwater? And we see that trace oxygen concentrations and DOC amendments support micropollutant biodegradation. And this is something already possible in existing groundwater aquifers. So that's kind of one way that it could be engineered in the field. So far I basically talked about the left-hand side of this this schema. So what's the combination of conditions required for micropollutant biodegradation? And there we saw that aquifer microbial communities seem to be able to degrade organic micropollutants, but they do need some amendments. So most likely oxygen and DOC are required for this. If I look at all of the results that we've done in many different studies, what I've seen is that the microbial biomass or diversity or a combination thereof really determines whether or not we see degradation in the lab. So depending on the samples collected and the quantity of biomass in there, we most likely have different diversities that result in more or less degradation observed. Moving forward then, our next question is to really understand if we're going to engineer this in the field, where should we engineer it? And we know because of the hydrology at these locations, we have very different flow rates depending on the depth. So we know close to the extraction well, we have high flow rates. Farther away, we have slow infiltration. And that, of course, affects then the flux of our substrates. So a biofilm existing in the shallow or deeper part of the aquifer has a different flux of substrates depending on the location. And so moving forward is really the question, how does this flow rate and therefore also the flux of substrates and the contact time with substrates affect micropollutant biodegradation? And one of the things that is coming up in the next year or so is building a very large simulated aquifer in our lab. So we plan to build kind of a 2D porous media tank and try to simulate this cross-section of an aquifer with different flow rates, but then in the lab. And I spoke with a couple of you about this today. But if anyone has experience with this or ideas for this, I'm very curious to hear, because it'll be a nice challenging project to do. So that's everything I wanted to say on groundwater for now. And then I wanted to shift over to rapid sand filters. And I'll kind of show in a moment, rapid sand filters for some of these things are not so different from groundwater. So it's also porous media with biofilms, etc. But first I wanted to briefly say something about rapid sand filter usage. So in the Netherlands, we use them both in surface water and in groundwater. I think many countries do this. And I'll focus today a little bit on the groundwater side. The rapid sand filters you commonly also use in surface water. One of the prettiest rapid sand filters I've ever seen is in Toronto. Here's the R.C. Harris drinking water treatment plant, beautiful old building looking out over Lake Ontario. And you can see here on the right then their rapid sand filters. So they're kind of straightforward technologies. Water goes through the filter and is backwashed every so often and is used for drinking water treatment. We've worked mostly with rapid sand filters treating groundwater. And groundwater, at least in the Netherlands, these rapid sand filters are used for a variety of, let's say, primary functions. So they're used for particle removal. They're used for chemical oxidation of a variety of reduced species like iron and manganese. And there's also a whole variety of microbial processes happening there. So we definitely have nitrification occurring depending on the intake water. Sometimes there's residual methane, so you can have methane oxidation in these systems. And then also oxidation of organic matter or other compounds. And so one of the interesting things is it's also a nice surface for microbial communities, but also has these iron and manganese oxides on these sand particles. And so one of our questions was, what can we actually remove already in a rapid sand filter? And I know I promised in my abstract to say quite a bit on sorption. And then when I was preparing the talk, I realized it was going to be hard to go too deep into the sorption with all of the other biodegradation. So I wanted to just briefly say kind of a brief interlude into physical chemical removal. So which compounds could be abiotically removed in rapid sand filters. And then I'll go back to some biodegradation things in rapid sand filters. So a little brief interlude into these removal processes. So we were curious, maybe I go back one. So we were curious to see if we look on this scheme, then we can expect different types of sorption or maybe even oxidative degradation processes by the iron and manganese oxides present on these sand particles. And so you're curious, what do we see if we really use field materials? So we collected from a drinking water treatment plant sand from 2 rapid sand filters, and at this location the water goes through 2 filters. So it goes through a primary filter, then it goes through a secondary filter, and we expect the primary filter more iron removal because that is more easily removed, and the secondary filter more manganese removal. We also expect in the primary filter more nitrification and a little less in the secondary filter. And this is when we characterized the materials, that's also kind of what we saw. So we saw much higher iron oxide concentrations in the primary filter than the secondary filter, but we actually surprisingly saw much more manganese in the primary filter sand than what I'd expected. That's for the iron and manganese side. If you look on the right-hand side, then you can see also all the other species that were present. And you can see in the primary sand, we had a lot more total organic carbon, so a lot more biofilm present, more phosphorus, more calcium, and a number of other species present there than in the secondary sand. And then we compared removal of micropollutants from those 2 types of sand to removal by synthetically made sand. So synthetic iron oxides or synthetic manganese oxides, just basically produced in the lab. So we oxidized iron or manganese as a coating on the sand and compared these. And like I said, this is a brief interlude into removal in rapid sand filters. So I won't go into all of the details. I'll just show kind of the overview of what we saw. So we saw removal of a variety of different compounds. And based on comparing all the different conditions, then we could hypothesize what's being removed under which conditions. So it seemed like for a set of compounds, we saw some chemical sorption onto iron oxides. So for a number of compounds like salicylic acid, 2,4-D, mecoprom, and caffeine, we saw a clear interaction with iron oxides. We saw for paracetamol, we saw sorption and oxidation by manganese oxides, and we could confirm this oxidation by measuring both manganese 2 and also degradation product from paracetamol. For benzotriazole, we saw some interaction with a type of, let's say, double layer interaction with calcium and phosphates. But we also saw that when we have high biofilm presence that really inhibited some of these sorption processes. So while we do expect the oxides themselves to do some sorption, if we have a lot of biofilm, this really inhibits it. So this was kind of the right-hand side of the schema. So what can we expect abiotic removal? And then our other question was, what do we expect for biological removal? So this biodegradation. And here we were really curious to understand how our substrate loading rate interacts with the contact time in the sand filter, and how do those together affect micropollutant biodegradation. And so for this, we set up rapid sand filters, so small rapid sand filters in the lab, so 3 different columns. We fed them with 1 microgram per liter of micropollutants, and then we had 1 column that was just the micropollutants alone in tap water. We had 1 column where we added a little bit of DOC, and then we had 1 column where we added a bit of ammonium. And these were really operated close to real rapid sand filter conditions, so with regular backwashing as is done in the field. And we tried to then examine which compounds are removed under which conditions. And we did this in 5 different phases. So we were really looking at changing substrate loading rates and changing contact times. And as you can see here, the conditions in phase 1, 3, and 5 are the same. So the substrate loading rate and the contact time are the same in phase 1, 3, and 5. So those were kind of our baselines. And then in phase 2 and phase 4, we changed this. So in phase 2, we lowered the DOC and ammonium loading rate. In phase 4, we lowered the DOC and ammonium loading rate and the micropollutant loading rate, and we increased the contact time. And we then operated phase 2 and phase 4 in different ways in order to achieve this. So in phase 2, we kept the same contact time, so the same flow rate, but we lowered the influent concentration of DOC and ammonium. So then you achieve a lower substrate loading rate by changing influent concentration. In phase 4, then we kept the influent concentrations the same, but we lowered the flow rate. So then you lower your substrate loading rate, you increase your contact time. And the kind of interesting thing is that you also play then in these with the ratio between your micropollutant and your co-substrates like DOC or ammonium, right? Because the concentration ratio changes in phase 2 versus phase 4. We did this for a whole list of different micropollutants. And as I said, all of them at 1 microgram per liter. So, and I have to really commend the PhD working on this, that he was able to run these reactors for quite a long period of time, so really months, and maintaining that 1 microgram per liter. So if we put all the phases together, our first kind of question was, which conditions are best for transformation of which compounds? And so if you can see here then removal efficiencies for 4 compounds in the 3 different columns. That's a control column, the DOC column, and ammonium column. And you can see that if we added DOC, we saw better degradation of paracetamol, 2,4-D, and mecopop. So that seems to indicate that a little extra DOC really improved the removal of those compounds, so maybe some sort of co-substrate or co-metabolic degradation of those compounds. We saw very clearly that benzotriazole was degraded very well under nitrifying conditions, so with the addition of ammonium. So that seems to indicate autotrophic co-metabolic biodegradation of benzotriazole. We also saw quite interesting for benzotriazole. So if you compare the control column to the DOC column, you can see very clearly that with the addition of extra DOC, we actually saw worse degradation. So that seems to indicate some sort of substrate competition between those 2 compounds. And this is something that we observed back also when we looked at the different phases. So you can see here in the top graph the DOC loading rates. So those were higher in phase 1, phase 3, and phase 5, lower in phase 2 and phase 4. And you can see in phase 2 and phase 4, we have more removal efficiency when there's less DOC available. So yeah, you can see this then most likely substrate competition between DOC and benzotriazole. as is also shown then if you put all of the data together. And so this kind of leads towards, as I said before, this idea of a feast. So if you give easily degradable DOC, then that substrate is biodegraded, preferable to the micropollutant. Continuing with benzotriazole, as I said, we also saw better degradation under nitrifying conditions. So you can see here on the left-hand side, the ammonium loading rate and the nitrification rates. And those were highest in phase 1, 3, and 5S. So that's when we had the most, added the most ammonium and therefore had the highest nitrification rates. And those were also the conditions in which we saw most benzotriazole biodegradation, so much higher. And you can see if you look, especially at phase 2, kind of a shift for the microbial community in activity. So at the beginning of phase 2, they have a little higher removal still, most likely because there's still some nitrification, some nitrifying activity, or some biomass, that's some more nitrifying biomass, I should say. And then as ammonium really is limiting for a longer period of time, then you see lower degradation. And this you can also see very clearly if you link it to your kinetic constants. So you can link your benzotriazole biodegradation kinetics to the loading rates and the nitrification rates. So that was kind of on the substrate loading rate side. The other thing we were interested in is contact time, because we expect for some of these compounds, maybe degradation is possible, but the kinetics are slow enough that we wouldn't necessarily see it in a rapid sand filter column being operated under real rapid sand filter conditions. So then we had this phase 4 in which we increased the contact time to 2.4 hours. So not realistic for a real rapid sand filter, but for our experiment, quite nice to do. And there you can see that metformin degradation really improved. So in phase 4, we see much more metformin degradation than in the other phases. So indicating that maybe the kinetics and the contact time are also very important. And we saw this notably for both the control column and the DOC column. So putting this kind of all together, we see for rapid sand filters a whole variety of possible biodegradation processes that could be occurring in these filters. So a combination of autotrophic, co-metabolic degradation, some heterotrophic activity, some substrate competition, and also really the important parameter of contact time. So this indicates there's definitely potential for biodegradation in rapid sand filters, and it's then the question, how to engineer this and how to control this in the field. So kind of going back to this original scheme of what can we remove in our existing treatment systems. So to kind of summarize, so we saw for groundwater systems, degradation is possible, but we definitely need to engineer this further. And the same thing for rapid sand filters. There is some possible removal, but this also needs some further tuning. And so kind of moving forward on this in the groundwater systems, I think it's really interesting to further explore the influence of the flow rate on the substrate flux. So to understand what type of flow rates and what type of substrate availabilities are required for degradation, and really explore further the role of DOC in the degradation process itself, but also, as you can imagine, adding DOC to groundwater changes your water quality and therefore could negatively affect your produced water quality. So this is also something we want to explore further. On the rapid sand filter side, the next steps are really to better elucidate this biodegradation sorption kinetics in real sand filters. We worked with field materials in this study, but it's quite challenging to actually work with real rapid sand filters because they are so protected by the drinking water companies. So something we'd like to do in the future is to work more together with them, maybe on a pilot scale at a drinking water treatment plant to try to let's say play with a rapid sand filter in real conditions. And then to kind of explore how can you change the operation in order to support micropollutant removal. I I'd like to end by acknowledging a whole set of students that did some really nice experiments in the lab, and also a number of financiers that supported a lot of this work. And thank you guys all very much for your attention. And I'd be happy to answer any questions.